Welcome everyone. Today we'll be talking about calculation of moment of inertia for various shaped objects, starting with the uniform rod and disc, and we'll also look at a cylinder if time permits, and then we'll go on to do for sphere and for spherical shells. Okay, and while we are doing this, we will also look at two theorems: the parallel axis theorem and the perpendicular axis theorem, because they are definitely helpful in making our life easier when we are trying to solve some of these problems. Okay, so until now we have looked at this quantity, which is moment of inertia, and we mentioned that this is a rotational analog for mass that we are considering in linear motion. Okay, so every time you're considering rotational motion, we have to think about what is the moment of inertia of the object. Okay, and these are some one-to-one relationships that we have looked at in Newton's second law. When we are considering linear motion, we have the relationship force is equal to m times acceleration. Okay, and this simply means that if we apply a force on an object of mass m, then it will do an acceleration a. Similarly, when you're doing rotational motion, if you apply a torque on an object of moment of inertia I, then it will do an angular acceleration of alpha. Okay, so there you go, one-to-one relationship. All right, similarly you have the relationship for momentum. When you are having linear motion, you have linear momentum, and that is given by p, which is the symbol for linear momentum, is equal to mass times velocity. And the one-to-one relationship with rotational motion is that the angular momentum will be moment of inertia times omega, and omega will be the angular velocity. Okay, and similarly you have relationships for kinetic energy as well, which will be 1/2 I omega square. Okay, so continuing along these lines, so you should realize that to calculate angular momentum and to calculate this kinetic energy, what we need now is we need to figure out what is the I for different objects. Okay, so we had already mentioned before that the I, which is the moment of inertia, will depend on the particular axis of rotation. Okay, so if you have a different axis of rotation, the values might be different, and if you have a different sized object, then the values will be different. Okay, so the formula that we use for moment of inertia, many objects, it is the sum of m of I ri square term. Okay, that means if you have one object of mass m1 and radius r1, then it will have m1 r1 square plus m2 r2 square and plus until you have all the objects. Okay, now we want to look at the same formula when we are following for continuous objects. All right, so for continuous objects like a sphere or a rod, this I will be an integral, and then we'll integrate over the entire mass, and then we'll have a term r square times dm. So for the first case, let's take the simple case of a uniform rod. Okay, so what does uniform mean? A uniform rod means that it has the same density throughout. Okay, so that is what we have to keep in mind. Now, as you noticed here, this rod is rotating about an axis that is going through its center. Okay, and that axis is perpendicular to its length. Okay, so this on top is the side view that you're seeing, and here is the top view. Okay, so this is the axis. Now it is going inside this plane of this screen. Okay, so again, what is the strategy to calculate the moment of inertia for this case? We know the formula that I will be integral of r square dm. Okay, 0 to m. That is the formula we have to use. Again, this is some rod, so we have to define the term density, which will be linear mass density. Okay, so we'll define linear mass density, which is given by symbol lambda, and that is nothing but the total mass divided by the total length of this object. Okay, so let's define m as the total mass, and let's say L is the total length of this rod. Okay, so now what we are doing is, just like before, we will consider a small mass element here. Let's consider small mass element here, and let's say this small mass element has uh, width of your dx. Okay, and for the width dx, it has some mass dm. Okay, so then what will be the value of lambda for the small mass element? Lambda will be your dm divided by dx. Okay, and here we can substitute this back into this equation. All right, so let's define where our origin is. So the origin, our axis, that is very important, so we have chosen it here. So this is a value of 0. Okay, and now we are trying to find the moment of inertia of this object with respect to this axis. Okay, so if I try to look at the length scale of this object from this origin, I am going all the way from minus L by 2 to plus L by 2. Okay, that is the total length that I am seeing with respect to this origin. Okay, so what will my integral become? My moment of inertia will become minus L by 2 to L by 2. Okay, r square, this is the position term, so I am measuring in terms of with respect to this origin axis, so I am measuring in terms of this direction, which is my direction in the x direction. Okay, so I will have a x square term here. Instead of dm, I can plug in lambda times dx. Okay, and now dx is varying from minus L by 2 to plus L by 2 with respect to this origin axis. Okay, and we have to be careful with our limits of integration. Okay, so lambda again is a constant term, it is a density term, so it can come out of the integral. Okay, so we'll have lambda, and in the integral we'll have minus L by 2 to L by 2, and here you will have x square dx inside your integral. Okay, so we know what lambda is. Lambda is just m over L. These are constant terms for a given rod. The mass and the total length is constant. Okay, so it stays the way it is. Integral of x square we know is x cube divided by 3. Okay, and now we have to apply the limits from minus L by 2 to L by 2. Okay, so let's plug the values in. So the first term will be, I'm going to take the 3 outside. Okay, the first term will be L cube by 8, which is this L by 2 plugged in here. Okay, and the second term will be minus of, there is a minus L by 2 here, so instead of x cube I have to plug in minus L by 2, and it will be a whole cube. Okay, so that is my expression. So I can solve it further. I get m divided by 3L, and on the top I get L cube by 8. Minus and minus sign, they cancel, so I will get plus. Again I have to take the cube of this function, so it is L cube by 8. Okay, so I have L cube by 8 plus L cube by 8, so that is 2 times L cube by 8. All right, so I have m by 3L, 2 times L cube by 8. All right, and now I can simplify it further. Okay, one L will get cancelled. Okay, so I will be left with L square term. M stays as it is. Okay, 2 cancels this 8. There is a 4 term here left here, and there is a 3. So I get ml square divided by 12. Okay, and that is my moment of inertia of a uniform rod that is rotating about this axis that is shown here from the center and perpendicular to its length. Now let's take the second example. This is now the moment of inertia of a uniform rod. Now it is rotating about its edge. Okay, and it's again perpendicular to the length. Okay, so you can imagine that you have, for example, a ceiling fan, and in the ceiling fan you have generally 3 spikes or 4 spikes. So you can imagine that you have a ceiling fan with just one spike. Okay, so you know a ceiling fan will look something like this, and you can get rid of the other ones, and if this is rotating, then it is rotating about this edge, and that's the same rotation that we are doing here for this rod. Okay, so this axis is fixed. Okay, and certainly now it is a different kind of motion that this object is doing, and the moment of inertia has to be different. Okay, so now our point of origin is here, that is a 0. again we will define that the total mass of this object is m and the total length of this object is L. Okay, so if this is 0, then this is r length L. Okay, and we already know I will be given as integral of r square dm. Okay, and we are integrating from 0 to m. All right, so again this is we can place it along the x-axis. So then this thing can be converted into integral of x square, r term will become x, and instead of dm we can again use the idea that lambda will be equal to dm divided by dx. So we can consider a small mass element here, okay, such that it has some width of dx, and if it has some width dx, then it has some mass dm. Okay, and the simplest way to understand this is, suppose this rod is of length 1 meter, okay, and it weighs, let's say, 1 kg. Okay, and now if I take the same rod and I split it into half, then the length will be 0.5 meters and the weight will be 0.5 kg because it is a uniform rod. Okay, and note that lambda for both the cases will be the same. Okay, so that is what we mean, the density doesn't change. Okay, so again dx is a small element here, and depending on what size of dx you choose, that much amount of mass you will get. Okay, so again we can plug this in, we can say this is lambda times dx, and now note that you are starting here, so you are integrating from 0 from this axis all the way to L. So you have to choose 0 to L. Okay, that's very important. So again lambda is a known value, lambda is just m by L, that is your linear mass density. So you can write m over L lambda, it will come out, and x square will become x cube by 3 after doing the integration, and you have the limit 0 to L. So again you get m by L, and here you get x, if you plug in the value of L here, you get L cube by 3 minus next term is 0. So essentially you get ml square divided by 3. Okay, so that is my moment of inertia for a rod now rotating about the axis from the edge, okay, and perpendicular to the length. Okay, so now again we are considering a disk, and this disk is rotating about again its center of mass, which is this center point here. Okay, and you can see the rotation that is happening. Okay, and so the rotation of this disk, and of course it is a uniform circular disk, uniform means it has the same density throughout, it will be about an axis through its center and perpendicular to its plane, right? So this disk is now in the plane of the screen. If we draw a figure something like this, and you can again see that the plane of rotation is this axis right here. Okay, so it's rotating something like this, and that is the disk. Okay, again strategy has to be the same. We have integral I will be 0 to m r square dm. We will have to consider a small mass element. Okay, but now it is not a one-dimensional case, it is a two-dimensional case. Okay, so you have to consider a ring that has a certain mass. Okay, so here in the dark two rings, you are seeing that this is the small ring element that we have considered. Okay, and this ring element has certain mass which is dm. Okay, and it will have certain area now because it's a two-dimensional case, which will be given by dA. Okay, and the ratio of these two will be again some density, and that is known as surface mass density, to be exact. Okay, and this is synonymous, you will use these ideas again in even electricity and magnetism, because if you have distribution of charges, then we talk about surface charge density. Okay, so it's the same idea here, we are talking about surface mass density. All right, now that is our sigma term. Good, now we need to know what is A. Okay, so if I start from this axis, that is my origin, and I'm going all the way to this radius of this disk, which is here, this value is r. Okay, so the total value is r. I can go in small steps in this direction. Let me call this axis as the x-axis. Okay, so my area of whatever I am considering as my radius of the disk will be some value of this value of x. Okay, what that means is, suppose I'm starting again here in the origin. If I consider value of x is this, then the area will be this term right here, which will be pi. Let's say this is x1, all the way from here to here is x1, and that is going to be my area. Suppose I had considered a larger value of x. Let's say I had considered this value, which is x2. Okay, and again I'm starting from the center. So then what would be my area? My area would be pi x2 square. Okay, so essentially what I'm changing is this value of x as I'm going around this axis. Okay, and when my x value is r, then I get the total area of the disk, pi r square. Okay, so now from here, this is my relationship of a is pi x square. So I can calculate that dA, which is the derivative, should be 2 pi x times dx. Okay, that will be just the differentiation of this function. Okay, 2 pi x times dx. Okay, so that is what I have to apply. And what are my integration limits? I am going from 0 all the way to r. And if I go from 0 all the way to r, I am covering the entire area of the disk. So I am going from 0 to r. I am going along this axis, which is the x-axis. So I get x square. dm is sigma times dA. Okay, and I can plug in the value for sigma. Sigma, in fact, can come out of this integral. So I can write it here. And I have dA will be 2 pi x times dx. Okay, so what is sigma? Sigma is just m over a. That is the standard formula, mass by area. So I can write mass by area. The total area is pi r square. So that is my sigma. I have integral 0 to r. 2 pi is constant, so it will just stay as it is. I have x cube term. Okay, so I can take the value of this x cube and integrate it. So I will get x raised to 4 by 4. Okay, so let's do that out. I have 2 pi, so 1 pi and pi will cancel here. So I'm left with 2. So I'm getting 2m pi r square. Okay, and integral of x cube is becoming x raised to 4 by 4. Okay, and now I have to apply the limits, that will be 0 to r. Okay, so again 2 and 4 will cancel, there will be a 2 left. So I get m r raised to 4 divided by r square times 2. Okay, and again r square, r raised to 4 will get cancelled. So I get m r square by 2. Okay, so that is my expression. I is equal to m r square by 2 for my value of moment of inertia of a uniform disk that is rotating about an axis through its center and perpendicular to the plane. Sometimes the situation might be that the object is not rotating about its axis of symmetry. Okay, then what will we do? Okay, so we can use the parallel axis theorem and the perpendicular axis theorem to do quick calculations of the cases where the object is not rotating about its axis of symmetry. Okay, so we have our object here. Okay, C is the symmetry axis. Okay, that's the axis through which you have you can imagine that the entire mass is concentrated. Okay, and now we want to find what is the moment of inertia about an axis that is parallel to this axis. Okay, and at a distance of certain length L away from this axis. Okay, and to do that, we have the relationship from the parallel axis theorem that I is just going to be the I through this center axis plus the total mass of the object times the distance square, and that will be equal to your moment of inertia about the axis at O. Okay, and the proof of this is very straightforward. You can quickly follow it here, that I we know is integral of r square dm, and if you decompose r in terms of the vectors and write it as r plus l for the situation where you're now calculating the position with respect to O, you get that I will be IC plus ML square. Okay. And we can word the parallel axis theorem much better by saying that if I is the rotation inertia about any axis and IC is the rotation inertia about an axis through the center of mass and parallel to the first one, but it is at a distance L, then this is the relationship of the parallel axis theorem. Okay, so let's apply it to a real case. We just did the case where we had the uniform rod that was rotating about this axis, right? And if you notice, this axis is parallel to the axis that is going through the center, okay, and it is at a distance of L by 2 from the center axis, okay, and we had already calculated the value for the I of C, okay. I of C was ml square by 12, right? That was the value that we had calculated in our first expression right here, okay. Let's plug that in this equation. So from our equation of parallel axis theorem, we know that I that is now going through this axis will be this I of C plus the total mass times the distance square, and the distance square is what? L by 2 square, okay. So let's plug that in. You get ml square by 12 plus ml square by 4, and if you take the LCM here, you will get basically you have to multiply this by 3 and you put a 3 here, and then the denominator becomes the same. So you get 3 ml square plus ml square becomes 4 ml square, and there you go. 4 by 12 is 3. So you get ml square by 3. Okay? And that is the result that we had just got when we tried to solve the case for the rod that was rotating about this axis, right? Ml square by 3. So again, we get the same expression, okay? So if you use the parallel axis theorem, our jobs become a little bit easier. You can plug in the values from the known values. As long as you know and remember the values, you can do that substitution, okay? Similarly, we have the perpendicular axis theorem, and the perpendicular axis theorem says that the sum of the moments of inertia for a three-dimensional body, okay, about its two mutual perpendicular axes is equal to the moment of inertia of the axis that is perpendicular to both these axes, okay. Simply in mathematical terms, I of the z, that is the moment of inertia along the z axis, will be the sum of ix plus I of y, okay. So we need to know either one of these terms so that we can calculate the other, okay. So again, let's take this again for action. Now we have the case where you have a disk, okay. However, remember we had the disk that was rotating about this axis of symmetry that was coming out of the plane of the board. Now you have the coin here that is shaped like a disk, and the coin is spinning out of the plane of the board, okay. So you can see that the two axes through which it is spinning, the first coin is spinning about this y prime axis, okay, that axis is fixed, and the second coin is spinning about this x prime axis, okay. So now how do we calculate the value of this? All right. Now these two cases are interchangeable. There is essentially no difference between I along the x prime value and I along the y prime values. Why? Because this coin is completely symmetric. Okay. So anything that is rotating about this axis and anything that is rotating about the x prime axis, essentially the rotation is the same, as you can see for both these cases. Okay. So here we can apply our formula for the perpendicular axis theorem, which says that your value for ix prime plus value of I in the y prime will be the value of moment of inertia in the third axis, which is I of z. And we had just calculated that I of z is ml square divided by 2. Okay. So from here, we can quickly get the relationship that 2 of ix prime or 2 of I y prime, because these two terms are the same, will be equal to ml square by 2, and so we can write that I along the xy prime or I along the y prime axis will be ml square by 4. Okay. So now we have a disk. Again, it is rotating about this OY axis. Okay. Now you know that this distance is d. Just give me the value of I of O. You see this rotation that is happening? This rotation is happening about this axis, y prime, ml square by 4. Now I'm asking you to make it rotate about the axis at the edge. Now it will be rotating about this edge. Let me call this y prime, for example. So I0 is nothing but I y prime. Okay. अभी हम लोगों ने थोड़ी देर पहले यहाँ का निकाला था. Along this axis, the value, let's say this is I1 was ml square by 4. That is what we got, right? And now I am calculating for a distance away from this, that is another at a distance of what? That is again at a distance of L from this center. Okay, so that will mean that my value is B is nothing but it is L only. Okay, so I of y prime will be ml square by 4 plus ml square. Okay, so my value should be an LCM of this, which will be 5 by 4 ml square. Okay, or L, or you can write D. L is the same as D or R or whatever. So this was a case where you're using your perpendicular axis theorem first, then you have to find I1, and then you use the parallel axis theorem, and then you find the value from this axis. You see, again continuing along these lines, we'll do one more derivation, and that will be the last one for today. Okay, and that is the derivation for a cylinder. Okay, so again we have a cylinder. It is a three-dimensional object. So now we have to use the three-dimensional density. So density in 3 dimension is written by this symbol rho, and it is just mass by volume. Okay, and what is the volume of a cylinder? It is pi r square times the height, which is, let's say, L. So we have to define that. Let's say this is the length of the cylinder. Okay, and let's say this is our center position. So let's say this value here is the value of your radius r of the cylinder. Okay, so now strategy remains the same. We have to find moment of inertia, that is integral of r square dm. Okay, and we are again integrating from 0 to the total mass. All right, so let's put this cylinder along an axis. Let's take this axis, which is the axis along x, and now what we have to do, just like before, is we have to define your small mass element dm. Okay, so let's consider a small mass element dm, and to do that, let's use a different color. So we'll have to use a mass element, let's say, of this sort. Okay, so that is going to be our mass element. Okay, and as this mass element is expanding, it is essentially covering your entire volume of the cylinder. Okay, and this mass element is extending all the way down, right here, all the way down here. Okay, there you go. All right, so let's see the relationship now. What is the value of this volume density for a small mass element dm? Okay, and again density will be dm divided by dv. Okay, now what is the volume for this small mass element? We have to find dv. Okay, now dv will be given by what expression? We have to use an expression for in terms of this x, right? So we have the area is pi x square times L. Okay, as the x increases to r, your value will be of the total volume, which is pi r square L. Okay, so that is my value of my volume. Okay. So small element dv will be 2 pi x L times dx. That is what it is going to be. Okay, and try to follow this step closely, right? L is the total length. It is a constant. It doesn't change. Pi doesn't change. What is changing? X is changing. As I increase the value of x all the way from 0 to r, I end up creating this entire cylinder. Okay, so that is what I'm doing. So I am choosing to integrate I when I'm going from the center position O all the way to my value of radius R, okay, as I am going along this x-axis, so I get x square. dm is rho times dv, okay, and so now I can substitute the value of dv, which will be 2 pi x L dx, right? And again, you get this term because if you take the derivative, your L is constant, pi is constant, and what is changing is x square. So you take the derivative of this, you get x dx, okay? So that is my term. So let's solve this out. Rho is your value of mass by volume. That is the definition. So I get m divided by the total volume is pi r square times L. Okay. Now I have 2 pi L. They are constant. They can come out of the integral. Okay. And I will get integral 0 to L. Okay. And I have x square and x. So I have x cube dx. Okay, so what do I get up? I get pi and pi will cancel, and I get L and L will cancel. So I get 2m by r square. So if I take the integral, I get x raised to 4 by 4, and then now I'm integrating from 0 to L. So I get 2m. So sorry, this is not L, it has to be R. Yes, thank you so much. So thank you very much. That is going to be R. So I get 2m by r square, and I get r raised to 4 by 4. I can cut this 2 out, r4 r square. So I get basically I will be m r square divided by 2. There you go. This is the expression for your moment of inertia of a cylinder that is rotating about this axis, which is, we call this axis as this y prime axis. Okay, the value should be mr square by 2. Whether it is one-dimensional case, we did the two-dimensional case, and we did the three-dimensional case, and in all the three cases we tried to integrate and create the entire volume of the object. That is our whole purpose. We are moving along the axis, we are creating this entire volume of the material, entire mass of the material, by integrating it along some axis. And once you do that, you create this entire three-dimensional cylinder, and from there you get the value of your moment of inertia.